Welcome back, everybody. Welcome back. In this video, we'll be starting section 3.3, which is about measures of relative standing and also box plots. And we saw in the last video, we were working on measures of variation like standard deviation, and those were ways of describing basically how spread out or how variable a set of data is. Here, when we say measures of relative standing, what is meant by that is we're interested in how a particular value compares to the mean in a particular set of data. And that depends on how variable the data is. So it depends on the standard deviation. Okay, so the main tool that we have in this section is the idea of a z-score or standardized value. And there are two different formulas here depending on whether you're dealing with population or sample data, but they're conceptually the same thing. It's the number of standard deviations that a given value x is above or below the mean. So we can think about a value being above the average or below the average. Okay, let's say that you scored, an 83 on a test. Okay, well, is that good or is it not as good? It sounds like a B. If the average is 80, then that says a different picture than if the average was 70, right? So knowing the distance from the mean is helpful in some way. It turns out that how far the distance is from the mean depends, or the usefulness of that depends also on what the standard deviation is as well. So the difference between the data value and the mean, so x minus x bar in the sample case or x minus mu in the population case, is divided by the standard deviation. So it's put in terms of units of standard deviations. How many standard deviations above or below the mean is this value? That's what the z-score is, and it's just called that because it's tradition to use the letter z for that. Okay. In this class, we have a round-off rule for z-scores. Z-scores in this class will be rounded to 2 decimal places. It's kind of, again, tradition to do that. I'll explain why we do 2 decimal places at a later date when we get into chapter 6. But for now, just know that it needs to be 2 decimal places. Okay, unless somehow you're told otherwise on my math lab or something. But otherwise, it's going to be 2 decimal places. Okay, so some properties of z-scores and then an example. A z-score is the number of standard deviations that a given value x is above or below the mean. Z-scores are expressed as numbers with no units of measurement. So again, let's think about that for a minute. Let's say that we're talking about heights of some plants in inches. The x then would be in inches. The average of some values that are in inches would still be in inches. And then the standard deviation would have the same units. And so it would still be in inches. If you have something that is inches divided by inches, those units are going to cancel out, leaving you with a pure number. So the z-score is just a plain number. So you're never going to have a z of 2.31 feet or something. Okay, it's just a number. Okay. A data value is what's called significant. Some books say unusual, but our book is going to say significant. A data value is significant if its z-score is less than -2 or is greater than +2. And what that means is basically that the data value is below 2 standard deviations below the mean or above 2 standard deviations above the mean. Okay, if a individual data value is less than mean, it's going to have a negative z-score. So that's important to know. A negative z-score is going to correspond to just being below the mean. All right, so let's try this a bit. We've had z-scores in earlier, or IQ scores in earlier examples. For this, it says that the mean is going to be 100 and the standard deviation 15. We want to just practice with the formula. We're going to find the z-score for an IQ of 125 and then one for 60. So we're going to make a little calculation. So z will be x minus x bar over sigma, or rather samples, so s, right? So here our score is 125, and then the mean was 100, and then we're going to divide that by the standard deviation, which was 15. Okay, so we have 25 over 15, and that's 5/3, which is about 1.66. Okay, so there's our z-score for an IQ of 125. That says that a IQ score of 125 is almost 2. It's a little higher than 1.5 standard deviations above the mean. Okay, so then next a IQ score of 60. So again, that's x minus x bar over, that's an S. That was a 5. There we go. Our x here is 60. Our mean is 100. That's divided by 15. And so we'll have negative 40 over 15. And that's negative 2.33 or 2.66. 2.66. All right, so that says that an IQ score of 60 would be more than 2 standard deviations below the mean. All right, so we've seen the definition of a z-score, and it tells us basically the number of standard deviations a data value is above or below the mean. In the past, we saw how you can use coefficient of variation to compare the variability of 2 data sets. We can use z-scores to compare individuals or individual results. So here's an example. Suppose that Maddie scored an 82 on an exam that has a mean of 71 and a standard deviation of 4. On the final, she got a 74, but the mean was 63 and the standard deviation was 7. So we want to know, did she do better relatively on the exam or on the final? Okay, so the thing is that on the regular exam, she scored an 82 when the mean was a 71. So 82 minus 71 is 11. So she scored 11 points over the mean. On the final, she scored a 74 and the mean was a 63. So again, she scored 11 points over the mean. The thing is that the standard deviation between the 2 tests is different. And so we'll see that she does better on one test than the other. So let's see. So let's calculate the z-score for the exam first. So z is x minus mu over sigma. This time I'm using population variables for this just because I wanted to have an example where we did. And I'm taking the population to be all the test takers. Okay. All right, so she scored an 82. The mean was 71. The standard deviation was 4. Okay, so then 11/4 is 2.75. So 2 3/4 standard deviations above the mean. So then for the final, z is x minus mu over sigma. I think it's a good idea to write the formula every time you use it, at least until you know the formula really well. Partly because it helps you learn the formula, and partly because it helps make sure you put the right things in the right places. So next, I want to be sure if I should have 74 minus 63 or 63 minus 74, right? I should start with the x value. So for the final, she got a 74. The mean, that's mu, that was 63. So having the formula written down there can help me get the right numbers in the right places. Okay, so now that works out to be 1.57. Okay, so she did about 1.5 standard deviations above the mean in the case of the final, and 2 3/4 standard deviations better than average on the exam. So she did better on the exam in a relative way. Okay, so what we're getting at here is that the difference of a data value from the mean, the meaningfulness of that, can depend on how spread out the data values are. So for example, let's say we have altogether different data sets now. And let's say that we know that the mean is here in both cases, and then we have a x value over here. Okay, so now the difference between the mean and the x value is the same in each case. but let's say label our two data sets A and B. For the first data set, let's make it so that the other values kind of all over like that. Okay, here's our X. Okay, there's one possible position, but then on the other hand, suppose that most of the data values were clustered around X bar, but X was further out compared to those. In this way, you can see that in the second case for a data set B, the score of X compared to X bar, it looks more meaningful than in the first case because it's like, more than like many other values in the data set. The difference, X minus X bar, is the same in both cases. It's just that if the values are really clustered together, then a large difference or deviation from the mean is going to be more meaningful than if the data values are kind of all spread out. Okay, so that's what we are seeing here in this case of Maddie and her exam and her final. Even though there was an 11-point difference between the two, the standard deviations were different. Okay, a couple more examples. So let's take number 1 first. So here it says, James Madison, the 4th president of the United States, was 163 centimeters tall. His height converts to a Z-score of negative 2.28 when included among the heights of all presidents. Is his height above or below the mean? Okay, well, we know his Z-score is negative. They haven't told us the mean. They haven't told us the standard deviation, but his Z-score is negative, so it has to be below. Okay, standard deviation is always positive, right? The ending of the formula has a square root in it, which makes it a positive number. And so the only way that the X minus X bar could be negative is if X is less than X bar, right? That would make the Z-score negative. So it's below the mean. Okay, how many standard deviations is Madison's height away from the mean? Well, that's just asking you a number. It's below, but it's 2.28 standard deviations below. Okay. The negative sign tells us the direction, and then the 2.28 is just telling us the magnitude of how far the guy's height is below the mean. Okay. All right, so let's say after I do our next test, which is coming up pretty soon, I convert everybody's tests to Z-scores. Which one of these Z-scores would you like if you could choose? -2, -1, 0, 1, or 2, and then y. Okay, so based on our discussion a minute ago with these presidents, Z-scores that are negative are below average. So I don't think I would like these. They're below average or below the mean. Okay, if you have a Z-score of 0, that is still the mean. And so if I get to pick, I would definitely rather be above the mean and by as much as possible. So I would like this one. Okay, this one says that you are, or your score is 2 standard deviations above the mean. Okay, so that would be the most desirable. Okay, because it's the highest. Is that a good score necessarily? Not necessarily, right? Because what if the mean is like 61 and the standard deviation is 2 or something, okay? So this would tell you that you are among the better of the students, or better scores among the students, having a score that is 2 standard deviations above the mean, but it doesn't tell you the absolute score, right? The mean could be low. Okay, another example. Okay, so here data set 31, which is about garbage weight, in the textbook lists weights in pounds of plastic discarded by households. The highest weight is 5.28 pounds, the mean is 1.911 pounds, and the standard deviation is 1.065 pounds. We're going to find the difference and then how many standard deviations that is. So at this point, you should pause the video, try it yourself, and then compare to what we get here. All right, so 5.28 was the maximum. We're going to subtract from it the mean, which was 1.911. So that will give us 3.369 pounds. Okay, that is our answer to A. And then for B, we want to know how many standard deviations that is. So that means that we're taking that difference and we're going to use that to just basically help us get the z-score. We have to divide by the standard deviation, which was 1.065. Okay, so that's 3.16. Okay, and that's unitless because it's a z-score. So it's a little over 3 standard deviations. Okay. All right, here's a question for you. Suppose that we found out that the S was actually 1.8. Would the z-score go up or down? Okay, so let's think about that and then we'll confirm it with some calculations. So here we found that a household with 5.28 pounds of garbage is like 3 standard deviations above the mean. So they throw away a lot of stuff. Okay, and that's according to having a standard deviation of 1.06. Okay, if it turns out that the standard deviation was really 1.8, that means that it's more variable. All the households are more variable in how much they throw away. And so the 5.28 is going to be less significant. So the standard deviation being bigger will make the z-score smaller. So let's go ahead and calculate that z-score. And so also, based on what you know about fractions, if you have a fraction and you take and make its denominator bigger, that's going to make the whole fraction smaller. If I could type, that would help. Okay, 1.87. Okay, so now the 5.28 pounds of garbage is really only a little under 2 standard deviations from the mean. Everything there? Yeah. All right, so the next part is about using z-scores to identify significant values. So we talked about the range rule of thumb before, how you can use approximately 1/4 of the range as a stand-in for the standard deviation. We can use the empirical rule. Data values are considered significant if there are 2 or more standard deviations from the mean. Okay, so as an example, suppose that human pregnancies last a mean of 281 days with a standard deviation of 13 days. Would a pregnancy length of 311 days be significant? And then what if the standard deviation were 15 days? Okay, so we're going to calculate this basically both ways. So first of all, with a standard deviation of 13 days. So again, that's x minus mu over sigma. Here I'm using the population values because the way that it's said, it sounds like all pregnancies, okay? It doesn't say we collected a sample of 100 pregnancies from the hospital or something. This is human pregnancies, so that sounds just like in general, okay? So a pregnancy length, that would be, this x value is 311 days. The mean is 281 days. And at first, our standard deviation is 13 days. Okay, I'm guessing it's going to be yes. Okay, 2.30 or 2.31. Okay, that's more than 2 standard deviations above the mean. And so based on that, I would say that's significant. Okay, so again, you should pause the video here and try recomputing this for a standard deviation of 15 days and see what we get. So here the only difference is our divisor is now 15 days. Let's see if that's enough to pull it under 2, right? In fact, it makes exactly 2 as it turns out. Okay, so that would still make it significant. Okay, if, well, that's enough of that. That takes us to the end of our first video here on section 3.3. In the next video, we'll continue with more examples at looking at whether a data value is significant or not. Okay, in the meantime, let me know if you have any questions and have a great day.